Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on Sanidinite Facies. I will cover this topic in two parts. In part 1, I will proceed under the following heads: introduction, general characteristic minerals, geological occurrences, important reaction, and mineral assemblages. Hope it will be useful for you. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly: A. Facies of low pressure, B. Facies of intermediate pressure, and C. Facies of high pressure. Mayasiro originally recognized three different facies series. First is geolite, prehanite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by kyanite, selemonite type. And third, an Abukama type of green schist, amphibolite, gaolite characterized by paragenesis of Andalusite selemonite type. The Abukama type is the name after the Abukama region in Japan, and it is similar to the Boken type of the Darillian. You have the facies of low pressure on your skin, increasing temperature of metamorphism as per Turner 1968. A. Albite epidote hornfels facies, B. Hornblende hornfels facies, C. pyroxene hornfels facies, and D. Sanidinite facies. If you will move from albite epidote hornfels facies to Sanidinite facies, the temperature of metamorphism is increased. The Sanidinite facies are found in the innermost of some contact areoles. Their development is favored especially by the shallow depth where pressure low and proximity to intrusive of basic magma, that is gabbroic intrusion, where temperature is very high, nearly 1000 to 1200 degrees centigrade. The Sanidinite facies was erected by Ascola to cover mineral assemblages whose mineralogical composition and geological occurrences show that they have formed at maximum temperature and minimum pressure of metamorphism. Ascola 1939. Rocks of these facies are restricted to xenolith in lava and dike rocks, and locally in contact rocks in the immediate vicinity of near surface intrusion. They are represented by xenolith in basic lavas or near surface intrusion, by fragments in tubes, and by the rocks of narrow contact zones bordering shallow basic pipes and volcanic rocks. In this latter situation, unusually high temperature have been maintained by continuous flow of magma along the contact. Characteristic minerals. A. In silica-rich peltic high temperature minerals like tridymite, sanidinite, sodium-rich anorthosite and mullite are common together with cauderite. B. As a result of partial or complete fusion of the pelites, a glass is sometimes present in rocks of this facies. These are called buccites, in which cauderite, corundum, mullite or tridymite are enclosed in glass. C. High temperature minerals are common, for example, tridymite, mullite, monticelite, millilite, larnite, sanidinite, anirich and orthoclase, etc. Cauderite, wollastonite and anorthosite are present in silicate assemblages. Mica, amphiboles and garnet is absent. D. There is a considerable replacement of calcium by magnesium in high temperature wollastonite. E. Grasularite is unstable and anorthite and wollastonite constitute a stable association. F. In calcareous rocks, high temperature minerals are present such as monticelite, millilite, spurite, runkinite, marvinite and larnite in order of increasing temperature of metamorphism. G. Micas, amphiboles and garnets are absent. The geological occurrences of Sanidinite facies is insignificant compared with what of the other phases of contact metamorphism, that is albite epidote hornfeld facies, hornblende hornfeld facies and pyroxene hornfeld facies. But it is so some interesting and unusual features of mineral paragenesis. Some of the characteristic phases are analogous with products of crystallization from melts or atmospheric pressure, tridymite, molite, 3Al2O3, 2SiO2, monticelite, CaMgFe, SiO4, fosterite, larnite, Ca2SiO4 and so on. The characteristic alkaline phase, sanidine, sodium, potassium, AlSi3O8, commonly a variety rich in sodium. Cordierite, wollastonite usually containing excess Mg or Fe+2 and anorthite are all typical of siliceous assemblages. Micaceous, amphiboles and garnets are absent. The only carbonate minerals is calcite. Important reaction. The important reaction occurring during Sanidinite phases are on screen. First, quartz give rise to tridymite at 870 degrees centigrade at atmospheric pressure. Second reaction, dapsite plus fosterite plus calcite give rise to monticelite plus CO2. Third, orthoclase give rise to sanidinite. Fourth, quartz give rise to tridymite, give rise to cristobalite. Fifth, 3-andalusite give rise to mullite plus SiO2. Sixth, grasularite plus quartz give rise to anorthite plus wollastonite. 7. Fosterite plus calcite give rise to monticelite plus CO2 plus periclase. 8. 2 wollastonite plus 3 calcite give rise to 2 spurite plus CO2. 9. Calcite plus millilite give rise to marvinite plus CO2. 10th, spurite plus wollastonite give rise to runkinite plus CO2. 11th, spurite plus wollastonite give rise to larnite plus CO2. Mineral assemblages. On the basis of ACF and Al2O3, MgO and SiO2 diagrams, the important assemblages are as follows. Peltic assemblages, tridymite, cordierite, molite, corundum, spinel, molite, cordierite, spinel, molite, glass. Quartzo-feldspathic assemblages. Number 11, tridymite, sanidinite, glass. Basic assemblages. Number 3, plagioclase, dapsite, hypersthene, calcilicate assemblages. Number 4, anorthite, wollastonite, dapsite. Magnesium assemblages. Number 5, inositite, cordierite, tridymite. Number 6, fosterite, spinel, periclase. Number 7, fosterite, cordierite, spinel. Number 8, fosterite, inositite, cordierite. Phi et al. In 1958 subdivided the Sanidinite facies into two types. First, monticelite, millilite subfacies and B, larnite, marvinite, spurite subfacies. The different assemblages in the two zones are displayed by CO, MgO, SiO2 diagrams. Calcareous assemblages. Second, anorthite, wollastonite, dapsite. 12, wollastonite, dapsite, tridymite. 13, dapsite, wollastonite, millilite. 14, dapsite, monticelite, millilite. These all occur in variable temperature. 15, wollastonite, millilite, calcite. 16, monticelite, millilite, calcite. 17, fosterite, monticelite, calcite. 18, fosterite, monticelite, calcite occur only at lower temperature. 19, wollastonite, runkinite, millilite. 20, runkinite, millilite, larnite. 21, millilite, larnite, marvinite. 22, millilite, marvinite, monticelite. 23, larnite, Marvinite spurite, 24 Marvinite spurite calcite, 25 Marvinite monticelite, 26 monticelite periclase calcite. Quartzo-feldspathic and peltic rocks in the Sanidinite facies in most cases have been brought to the point of partial fusion. These are bruchite rocks in which minerals such as cordierite, corundum, mullite or tidymite are enclosed in a glass. When the crystallized phases are minerals not commonly found in common igneous rocks. It is customary to consider the assemblage as metamorphic in the Sanidinite facies, but quartzo-feldspathic rocks at only slightly higher pressure may become converted to what can only be considered igneous products, namely granophyres. Even at near surface pressure, metamorphic rocks merge into igneous rocks via the Sanidinite facies. Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. Today, in this course, I will deliver my lecture on Sanidinite Facies Part 2. In this lecture, I will proceed under the following heads: peltic and quartzo-feldspathic assemblages, physical condition of metamorphism, and finally summary of the facies. Hope it will be useful for you. Try to be regular in course. Classic example of the Sanidinite facies paragenesis are the suits of peltic xenolith in trachytes tuff of the Lesser Sea region, Germany, bronze 1911, and in minor theolitic intrusion on the Scottish island of Mull, Thomas 1922. The Lesser Sea rocks have been modified by the neometallitic introduction of sodium and include various combination of sanidinite, cordierite, spinel, hypersthene and sillimanite. Many of the rocks have been reached equilibrium at low pressure and contain unstable relics, garnet and sterolite from an earlier facies. In Mull xenolith, representative assemblages are: first, corundum spinel anorthite; second, cordierite mullite; third, cordierite glass; and fourth, mullite glass. In quartzo-feldspathic xenolith, in Mull suits, tridomites have crystallized around nuclei of unfused quartz enclosed in glass. Generally, similar assemblages have been described by exceptionally illustrated by Cyrillic in 1962 from the quasi-recent basaltic province of Auckland, New Zealand. The agents of metamorphism is alkaline olivine basalt. The metamorphic rocks are xenolith in lava flow and pyroclastic deposits and backed sills intercalated between or underlying surface flow. So this is a clearly demonstrated case of metamorphism near atmospheric pressure, as is usually the case in Sanidinite facies. Reciprocal diffusion has modified both the metamorphic rocks and intermediate adjustment basaltic magma. The result is relatively enriched of the metamorphic rocks in calcium, magnesium and iron with complementary loss of silica and alumina. The principal metamorphic assemblages are mullite glass, second, cordierite mullite glass, third, cordierite mullite, fourth, cordierite quartz, fifth, cordierite plagioclase, calcite, sanidinite, clinopyroxene, sixth, sanidine, pyroxene, hematite glass. The sanidine is the high temperature polymorph of quartz in mainly assemblies that is in the sanidinite, appear to have inverted from thermite that had crystallized in the first place from glass. There are many records of basic hornfels formed by recrystallization of basalt on the walls of conduits of the shallow basalt magma chambers. Xenolith of such material in the Auckland basalt shellacks in 1962 consists essentially of calcic plagioclase and hyperthin ejected block from the wall of the Kulik crater vent in Hawaii, Tele in 1958. Consists of plagioclase, anorthite 62, augite, hyperthin with minor pseudobrochites and tridymite. Relicts phenocryst of olivine are in process of conversion into hyperthin magnetite by a reaction involving oxidation of iron. Lindsley in 1958 have recorded a suite of unusual minerals assemblages resulting from low pressure metamorphism of basalt and its associated weathering products adjacent to and within a ternary plug of olivine diabase in Antrim, Ireland. First, olivine clinopyroxene plagioclase magnetite ilmenite. Second, hyperthin plagioclase magnetite ilmenite pseudobrochites. Third, corderite plagioclase magnetite, hematite, pseudobrochites, tridymite or cristobalite, molite. The sequence 1 to 3 represent pre-metamorphic compositional changes from olivine basalt to a montmorillonitic weathering products. A second suite of assemblages, very rich in Fe and deficient in silica, has formed by marginal metamorphism of a engulfed block of porcelainite. This represents a initial lateric weathering product of basalt. Fourth, a corundum hematite pseudobrochites. B. Corundum molite hematite magnetite. C. Molite hematite cristobalite or tridymite. Fifth, A. Corundum hercinite ilmenite magnetite. B. Corundum molite hercinite ilmenite magnetite. C. Molite hercinite cristobalite tridymite. D. Molite hercinite corderite cristobalite or tridymite. E. Molite corderite cristobalite or tridymite. Assemblages in 4 are highly oxidized. Both corundum and molite carry significant Fe+3 assemblages. In 5, which occur closer to the contact, have been reduced to a comparatively low oxidation ratio. Corundum and molite are normal. Corderite appear in assemblages with appreciable MgO. According to Ascola in 1939, the characteristic silica saturated assemblages in calcareous rocks are combination of wollastonite, anorthite and diapsite. Grassolarite, which is so common in hornfels of other facies, is notably absent. In its place appear the pair anorthite wollastonite. The assemblages once thought to be critical of Sanidinite facies has now been recorded with associated quartz in situation that indicates pressure certainly much higher than those of the Sanidinite facies. It has been observed in some granite areoles in the California coast ranges, for example near inversions north of San Francisco, and it is widely developed adjacent to granite platoons of Naga Parvat in the Himalaya, Mies in 1964. Anorthite wollastonite may also provide characteristics of the pyroxene hornfels facies. Silica deficient marbles and dolomitic marbles in the Sanidinite facies display mineral assemblages unique in metamorphic patterns, as Seward's Hill in North Ireland chalk with enclosed nodules of the flint has been metamorphosed at the contact with intrusive of diabase. The assemblages developed by reaction between the flint and calcite has been recorded in detail by Telly 1929-1942. They have corresponds to the products of the later steps in Baumann in 1940. Sequence of progressive reaction with rankinite has an additional phase, since the reaction has involved the outward diffusion of Si from the charred nodules and inward diffusion of calcium and magnesium from chalk. Each metamorphic nodules is now concentrically zoned as to compositional and mineral paragenesis. A remarkable paragenesis occur in block of limestone engulfed in flow of lucite tephrite near Mayen in the lesser sea region. These rocks have a very high ratio of calcium ratio magnesium, mostly 20 to 50, and contain 10 to 20% SiO2 and a few percent each of Fe2O3 and Al2O3. Neglecting late hydration phases, there are two group of assemblages. First, wollastonite, millilite, magnetite or spinel. The minerals brown millilite, Ca2, Al, Fe2O5 and mearnite, Ca12, Al14, O33 are unique in that they are otherwise recorded only as a constituents of cement clinkers. The appearance is attributed to gas pressure even lower than those normally developed in shallow contact zone, as exemplified by Seward's Hill. Orthopyroxene is confined to the orthopyroxene subfaces of the potash feldspar, cordierite, hornfels facies and to sanidinite facies, characterized by higher temperature yet and by low, often very low S2O pressure. The temperatures are in excess of 870 degrees centigrade. The PT field of the sanidinite facies overlaps into that of fusion of peltic rocks and quartzo-feldspathic rocks. The reaction quartz give rise to tridymite 870 degrees centigrade at atmospheric pressure. Second important reaction, diopside plus phosphorite plus calcite give rise to monticelite plus CO2. Suggest temperature of more than 800 degrees centigrade for the beginning of the sanidinite phases. The upper temperature limit may be indicated by 1000 degrees centigrade. The reaction spurite plus rankinite give rise to larnite plus CO2. The field occurrences indicate that pressure must have been less than 500 bars in sanidinite phases. The course content on metamorphic low pressure sanidinite phases begin with the introduction, followed by the description of sanidinite phases, the general characteristic minerals in this phases, geological occurrences, important reaction and the chemographic phase relation with the help of ACF, AKF, Al2O3, MgO, SiO2 and CO, MgO, SiO2 diagrams, and the mineral assemblages for peltic, basic, calcareous and silica deficient rocks, and finally the physical condition of metamorphism during sanidinite phases. The PT field of the sanidinite phases overlaps into that of fusion of peltic and quartzo-feldspathic rocks. For further studies, please read the textbooks, references and links given in the text. Thank you very much.